Welcome back to Calc AB, everybody. Today's topic, 4.5, part 3. Example 9, a pile of sand. This would be Chrome problem number 1. So sand is poured on a beach, creating a cone whose radius is always equal to twice its height. If the sand is poured at a rate of 20 cubic inches per second, how fast is the height of the conical pile changing at the time the height is 2 inches? All right. So here again, we want to figure out the given information. So, well, first of all, let's draw a picture, right? Let's see what's going on. So this is the sand is being poured and it's in a conical shape, right? We have a radius. We also have a height on this shape. And that's pretty much the only two things we need to figure out in order for us to be, or in order to have, in order for us to find the volume of a cone, right? Or the surface area. So here, the given is that they're telling us that the sand is being, well, first of all, that the radius is always twice the height, right? So we're going to say R equals 2H. And then also they're telling us that the sand is poured at a rate of 20 cubic inches per second, meaning since we have the units cubic inches, that means it's a volume, right? If we had square inches, then it would be pretty much an area. If it didn't have a unit right there, if it was just a single unit, then it would be pretty much like a measurement only, right? So here in this case, we're looking at volume. So dV dt equals 20 cubic inches per second. All right. And then we need to find, in this case, we need to find how fast the height is changing at the time the height is 2 inches, right? So we need to find dHdt when h equals 2. All right. So here we need to, the equation we're going to need for this, the equation is, since we have a volume, that means we're going to be using the volume formula for cones. And in this case, it's V equals 1/3 R pi R squared times H. All right, so it's very important that we try to eliminate as many variables as possible so we can make our job a lot easier. All right, so here, one of the things we want to do, since we know R is equal to 2H, I'm going to substitute R squared with 2H. All right, so in this case, we have V equals 1/3 pi 2H squared times H. All right. Now, I want to do this right now because I want to avoid me trying to do the product rule, right? Because there is a product here. And then doing this substitution right now allows me to pretty much just have one variable right there, which is going to make it a lot easier. Okay, so we continue. Let's do it right here. So we have, we take the derivative of this, right? Let me simplify this a little bit more. So we end up with V equals pi over 3. And then 2H squared times H. So that would be 4. So that would be 4 pi over 3. And then H cubed. And then we take the derivative of that, which is going to be dV dt equals 4 pi over 3, which is a constant, times 3h squared times dH dt. All right, and then we start to do our substitution. So we're able to solve pretty much for dH dt. So here dV dt is equal to 20 equals 4 pi over 3. And then, well, actually, this cancels with that one nicely, right? Here we go. That's going to be 4 pi h squared, which in this case is 2 squared times dH dt. And then from here, we're going to simplify a little bit further. So it's going to be 20 equals 4 times 4, which is 16 pi times dH dt. Divide both sides by 16 pi. All right, we simplify and we find that dH dt equals, that'll be 5 over 4 pi. So we can say pretty much that the height, right? We want to write a statement. The height is changing at a rate of 5 over 4 pi inches per second at, well, I think that's it. That's all we need pretty much, right? So the height, I actually forgot the height of the sand pile, right? Important, the height of the sand pile. We need to include what we're talking about. The height of the sand pile is changing at a rate of 5 over 4 pi inches per second. All right. So now let's look at problem example 10, a draining tank water. So cone problem number 2. So in this case, we're pretty much looking for, right? So it says water is draining from a conical tank with a vertex down at a rate of 2 cubic meters per second. The tank is 60 meters high and its top of the radius is 4 meters. How fast is the water level falling when the water level is 12 minutes high? All right, so the CR of information. So the vertex is down, and right, we're going at a rate, it's decreasing at a rate of 2 cubic meters. So the volume is decreasing at a rate of 2 cubic meters per second. And then they have specific measurements for the cone, right? How fast is the water level falling when it's 2 meters high, right? So let's draw our picture. Right, the vertex is down, and then remember we have a radius, right? And then we have our height. And then say it's when the water is like right here, right? And then it's pouring out of here. So the given information, again, let's write that down first, the givens. In this case, we're given that dV over dt would be equal to, it says, is the water is draining. Since the water is draining, that means that it's decreasing. So we're going to say negative 2 cubic meters per second. All right. And then they're also telling us that the height of the tank, right, the full height of the tank is 16 meters, and then the radius is 4 meters, right? That's just the tank. Okay. And they want us to find how fast is the water falling when the water level is 12 meters high. So how fast is the height changing? So dH dt equals something when h equals 12. All right. So here again, we're going to use a similar triangles in this case. This is going to be a little harder to set up, right? So because they're not telling us that the radius is twice its height or anything like that, right? So what we're going to do here is, since we know that the tank is 16 meters high and then 4 meters in the radius, we can use that information to figure out something that we can again substitute for either R or H, right? So let's do that first. So we know that the ratio, right? So that the ratio of this is going to be 12, and I know that this one is 16 in total, right? And then from here to here is 4. So I know that the ratio of these two triangles has to be equal, because again, they are similar triangles, right? They have the same angles, 90 degrees right there, and then these two angles are also the same. Since we have similarity established, we can pretty much use that. So we can say that R over H equals the same parts, right? 4 over 16. 4 over 16. And then here, I think it would be a lot easier for us to solve for R. Just multiply both sides by H. So R equals, in this case, H over 4, right? Or 1/4 times H. So now we can use that information to pretty much figure out how fast the height is changing. All right. So here it's more convenient to solve for h because, again, we have to find dh dt, right? So again, we're going to use the same formula. So we're going to be using v, right? So that's the equation. V equals 1/3 pi r squared times h. Again, we're going to substitute. So that's going to be 1 pi over 3. R squared is now h over 4 squared times h. And then this is equal to, so the volume now is equal to, it's going to be pi over 12. Oh, sorry, pi over 48, right? Because it's 16. And then on top, we're going to have h cubed. And then we take the derivative of that, of course. That's going to give us v dv dt equals pi over 48, which is our constants, right? And then that would be times 3h squared times dh dt. And in this case, h happens to be 16 right now, right? So we can use that information as well, right? So we substitute everything back in. We know that dv dt is changing at -2, so -2. And then here, pi over 48 is a constant, so that still remains. And then the height is pretty much 16. So that would be 16 squared. And then, no, wait, it's not 16 squared, sorry. The actual height at h equals 12, right? So h equals 12. So that would be 12 squared. And then times dh dt, which is pretty much what we're trying to find, right? So here again, simplify. And then 3 goes into 48. That's 16. 16 times -2 gives you -32. Equals 144 times dh, 144 pi times dh dt. Divide both sides by 144. And then we end up with pretty much -32 over 144 equals pi dh dt. So we can say that dh dt is equal to, once we simplify, -2 over 9 pi meters per second. So our conclusion is that the water level is falling at a rate of -2 over 9 pi meters per second.